Okay, hi everyone. This is chapter 28, 4 sections. We're going to talk about particles inside the magnetic field and motion of these particles inside magnetic field. We're going to take maybe 3 or 4 applications. And then the last part, we're going to introduce magnetic force acting on a current carrying conductor. When you have a conductor, current inside it, what's going to happen if either you put this conductor inside magnetic field. Okay, so we're going to start with some introduction, some history about magnetism. It's a concept, or it's a phenomenon known in many cultures. 13th century by Chinese, by my pen doesn't work. And of course, a lot of development happens. The most recent development in magnetism or electricity and magnetism, credit actually goes to European. So there are many scientists contributed into development, discovery, and also finding the relationship between electricity and magnetism. For example, the famous scientist Ørsted is credited for finding the relationship between electricity and magnetism. Before his time, people knew that these two phenomena, electricity and magnetism, were two separate phenomena, two separate things. But he's the one actually found that if you have a wire passing, a current passing through the wire, this will affect compass that's closer to the wire. So for example, if you have a wire made of any conductor, any material, if you pass current through it, and if you put a compass close by to this wire, the compass will be actually deflected. It will rotate into a certain rotate, and it will stop at certain position. So he knew that this current, which is the source of electric field, has something to do with the magnetic field. Maybe he knew that the current, the wire, create a magnetic field around the wire. Of course, other big names such as Faraday. Faraday is credited for his famous equation in creating electromotive force, electricity from changing the magnetic flux, which most of our, or actually all our technology now depends on generation of electricity simply using Faraday. Okay, some more introduction into the topic. We're going to now talk about something called a magnetic pulse. So if you consider a piece of magnet, it has two poles. One side we call it north, one side we call it south. If you break this magnet into two pieces, you still have north-south, north-south. So if you keep doing this, if you keep breaking this magnet smaller, you always end up having two poles, north and south, south and north. But actually, if you remember, in electricity, that wasn't the case. In electricity, we used to solve many problems, and we used to say positive charge, isolated, or negative charge, isolated. But in magnetism, these two poles, which is kind of, let's say, similar to positive charge and negative charge, just in names, these two poles are always together. Okay, scientists, to be honest, physicists believe that monopole exists, but experimentally nothing like this was discovered so far. So if you have any needle like a compass, and any compass, if you study it, it's always, one side we call it north, one side we call it south. The name north and south simply came because when you have a compass, such as this compass here, it's suspended in the air in our planet. Okay, so we know that this compass, one side we call it south, one side we call it north. The reason is, when you suspend this compass in the air, it will rotate freely, and then after a few seconds, it will orient itself in such a way that one side will orient itself to the north geographical pole, okay, and one side will try to be away from the north geographical pole. And just for the info, our planet, so here we call it north geographical pole, but actually it's a south magnetic pole. So this is wrong, actually. It's south magnetic pole, and here we call this side south geographical pole In geography, we say north and south. So this is north, this is south. But when it comes to magnetism, because our planet has magnetic properties, our planet can be modeled as a bar magnet, which is shown inside the planet. But it just happened in such a way that the south will be at the north geographical pole and the north will be at the south of geographical pole. Every 100 million years, this actually gonna rotate. Okay, every 100 million years, the south will be north, the north will be south. Even as we speak now, this is not exactly fixed, so there is a little bit fluctuation back and forth in this angle. Okay, a little bit fluctuation, but historically, every 100 million years, this poles, Earth magnetic pole, will reverse. Okay, but for now, we know our north geographical pole is actually south. Therefore, if you suspend a compass like this, one side orient itself toward the south magnetic pole, which is this. That's why we call this side north, because it's trying to get closer to the south magnetic pole. Okay, that's the name actually came from this. Okay? The name of the compass, North Pole, South Pole, simply came from how this compass, if you suspend it freely in the air, how this compass, orient itself toward the Earth magnetic pole, south and north. Okay. So we have, similar to electric field, we have actually magnetic field. So let me just take you back to before midterm. So before midterm, we know that if you have a positive charge or negative charge, doesn't matter, around the positive charge, there is an electric field. Right? There's electric field going around all the directions. Now, this electric field, we could define it, we cover a few chapters, we solve problems and so on. But now what happens if this charge moves with a speed or velocity v? In this case, actually, let's say the q, let's assume that q is moving forward or backward or whatever the direction v. In that case, that charge around it will be surrounded by another field, that field called magnetic field. Okay? So the region that's surrounding any charge in motion, this is called magnetic field. Means that charge which is in motion, it still has electric field and it has magnetic field. So if you, in this case, there is no magnetic field surrounding this charge because the charge is not in motion. But whenever the charge starts moving, okay, the magnetic field right away get created and will be surrounding that charge. So this is important differentiation between the source of electric field and the source of magnetic field. In the case of electric field doesn't matter or doesn't care if the charge is in motion or stable, not moving. In both cases there is electric field, but in magnetism, magnetic field only surrounding moving charge. Okay. The symbol of magnetic field or the symbol of electric field was E, the symbol of magnetic field is B. Okay. So we're gonna deal with magnetic field B. The same way we discuss electric field, we're gonna discuss magnetic field. We're gonna deal with equations, and you will see in few minutes the equation for the magnetic field a little bit more difficult than the equation for the electric field. So we're gonna discuss this. Okay, again, similar to electric field, let me just take you back a little bit backward through electric field. If you have two charges, positive Q, negative Q, or together or maybe isolated, there is an electric field line. We call, in the case of positive charge, the electric field line will go away from it. In the case of negative charge, electric field will go toward it. So for example here, electric field goes this way, goes that way, and so on. You could draw this. So we call this electric field lines. Electric field line. If you remember before midterm, here this direction simply refers to the direction of a force that affecting on a test charge. So for example, if I am a test charge and I place myself here, definitely I'm going to move this direction. The reason is this charge is positive. I am also positive, so this charge doesn't like me. So the force will be that direction. This is negative, this is positive, so this charge will need to go this direction. So the resultant of these two forces will be into that direction. We have kind of similar idea we have also magnetic field line. So when you have a bar magnet, which is shown here, so instead of positive Q, negative Q, in the magnet we have north and south. You will notice that there are field lines. These field lines called magnetic field lines. These field lines originated from the north. Look at the arrow. Notice the arrow going from the north and ending at the south pole. Okay. If you follow any line, so for example here the arrow moves that direction, so originated from north pole and ending at the south pole. If you remember again, right now we said that point here, if you put a test charge of positive, it will move that direction. If you put a test charge here, it will move that direction. In magnetism, we are not dealing with test charge, we're dealing with a compass. So if you put a compass in that location, the north pole of the compass will direct into that direction. If you put it here, it will go that direction. If you put it here, it will go that direction. Again, remember, what is compass? Compass is just like a needle shape metal. So it has, it's a magnetic piece. One side is negative, one side is positive. Okay. Let me, maybe, I don't know if you could see the screen. Let me just write down compass. I'm not sure if you see the screen or not, but these are compass, okay? People use this, for example, maybe this is something you know it. People use this compass to find the direction of some holy places, okay? So the needle inside, this red and white color. I'm actually on Google, so I don't know if you see this image or not. Let me see if that's the case. Yes, you see it, okay, good. So that compass simply, that needle, the red and the white, if you put it freely somewhere, it will find its direction, and somebody marks some numbers, this is altitude or latitude, and they put a sign that, this is a special place. So this is a compass. People use it. People used it long time ago, as we mentioned in one of the slides. The origin for the compass either goes back to Arabs or Indian. So people knew about this a long time ago. Let me go back to my. And actually, you could show this in lab. For example, if you have a piece of magnet, which is this one, it's a north and south. If you put it on a piece of paper on a table and spray some, iron powder on it. If you spray some iron powder on it, you will actually kind of see the lines. The magnetic field line. This is representing the magnetic field. So what does that mean physically? It means there is a magnetic field here, there is a magnetic field here, looks like there is a strong magnetic field here, there is a strong magnetic field here. And that's a typical thing. Close to the poles, there are, magnetic field gets stronger and so on. Now, if you, again, if you do this experiment multiple times with different procedure here, in this case, you have two magnets. So if you put the north of one of them facing the south of the other one, you will see how beautifully these lines actually oriented, right? And so on. So this is something could be demonstrated in lab. So in summary, similar to electric field, magnetic field also can be represented by electric field lines. These lines are imaginary in space, but you could demonstrate it in lab, as we discussed, okay? Now, we're gonna proceed similar way, very similar to the way we proceeded in magnetism, right? We define electric field. So again, every time I talk about the topic, I want to take you back to electric field so you could have a connection between these two topics. How we define electric field? So we define electric field, we simply say electric field do exist in some place. Okay, we know electric field exists in some place in this room, for example. If we have a charge we placed in that room, in that space, and a force affecting on it. Okay, that's how actually we define electric field. We simply say force is equal to QE. So let me explain more this. If I have a charge and I placed it inside electric field, a force will be affecting on that charge. If the force was not affecting on the charge, we say there is no electric field there. Okay, so that was the whole idea. But I want you to focus on that equation. That equation was very easy because the direction of the force is directly with the direction of the electric field if Q was positive, and its opposite to the electric field is Q was negative. Easy peasy, right? In magnetism, we have similar kind of equation, but a little bit harder because we're going to deal with that. It's not straightforward because, as we discussed a few minutes ago, in magnetism, the charge has to be in motion. So in magnetism, in order to define, let's consider this case. Let's assume we have a charge, and that charge is moving with a velocity v. Why we introduce velocity? As I just mentioned, in magnetism, the charge has to be in motion. Okay, that's in motion and inside magnetic field to be experienced by a force. So now let me say it again. Let's consider we have a charge. That charge has the velocity v, and it's inside a field. That field is external field. Okay, let's say there's a magnetic field in the room, and the charge just moving inside this magnetic field. A force will be created on that force. That force called, by the way, here the force, usually we call it F sub E, means electric force. But before, because we didn't know there is another force, we just called it F. Here, the force, we're going to call it F sub B. Okay, F sub B. The force actually defined as the following equation. It's equal to Q V as a vector cross B. So it's a cross product. And I think everybody, I mean, all of you know how to define cross product. So A cross B. What's the result of A cross B? It's another vector. We call it C. But that vector C, from your math skill, C is actually perpendicular to A, and C is perpendicular to B. Let me take you back here. Force here was with the direction, the same direction of electric field. If Q was negative, positive, and it's up with the same direction if Q is positive, and opposite to it if Q is negative. But in this case, our CAB, A is our velocity. Okay, this is A is just symbolic, math symbolic, but here in physics, there's a meaning of those. B, letter B, in this case is magnetism. Okay, and C is simply the magnetic field. Now Q is just it doesn't change anything. It's just a constant, right? It's just a number. It's just a constant. So let me write it again. So the magnetic field B can be defined Q V cross B. So what does that equation mean? This equation simply means if you have a charge, this charge moves with a velocity v inside a magnetic field, a force will be created on that charge. And the force is equal to this equation. Now this is cross product. You all know cross product has two things, right? Magnitude and direction. So the magnitude of the force is simply equal to QVB sine theta. So what is theta in this case? Well, theta is between the two vectors. Theta is the vector between the velocity and the magnetic field. So let's take a couple cases. What if the theta was equal to 0? Means a charge moves with the same direction of the magnetic field. Nothing will happen on the charge because sine theta is equal to 0. Again, if the charge moves opposite to the magnetic field, nothing will happen to it. No force, no magnetic force will be affected on that force, on that charge. Okay, that wasn't the case in electric field. But if sine theta, the maximum value of sine theta is 1, means if the charge moves perpendicular to magnetic field, the maximum magnetic force will be affected on it. So that force, it's variable, right? It's of course, I say it's variable, mean that force depends on many parameters. One of them is theta. Okay. So the maximum value for the force if everything else constant, is when the theta is equal to 90 degree. So this is the magnitude of the force. So the magnitude of the magnetic force sometimes is equal to 0, sometimes equal to the maximum, sometimes equal to any value in between. Okay. So this is important. Now, what about the direction? Okay, so we need to figure out what's the direction of magnetic field. Well, the direction of the magnetic field, we could easily use a right-hand rule. I'm sure some of you may be taken this in math. If not, don't worry, we're going to talk about right-hand rule. So there are many ways to use right-hand rule in magnetism. So for example, here, this is one configuration and this is the other configuration for using right-hand rule. So let me write the equation again here, and then let's follow it. It's equal to Q V cross B. We will not focus on Q because Q is just a number, it's just a constant. Okay, it does not affect the direction in this case. Actually, it does, because Q might be positive or negative, but we're going to talk about this. So in order to use right-hand rule, there are different ways to do it. One way is you use your finger, or you put your fingers on the velocity vector, and you try to curl or spin your fingers toward the B. Your thumb should give the direction of the magnetic field if Q is positive. If Q is negative, you simply say the direction of the magnetic field is opposite. So let's take a few examples. Let's take this example. So we have a charge. I want you to think about this. There's a charge. Looks like the charge want to move this way. The charge want to move that way with a velocity v, but there's a magnetic field directed this direction, B. So according to that equation, something has to happen to the charge. A force will be affected on that charge, okay? Because there's an angle between velocity and the magnetic field. So in this case, I'm going to put my fingers, 4 fingers, on the direction of B, and then I try to rotate my fingers toward B. So my thumb going to be in that direction. Now this is the case if that charge was positive. If the charge was negative, you simply say the direction of the force is opposite to that direction. Okay. Let's take more cases. For example, here I just took it from, so the credit for this picture goes to Wikipedia. Other people maybe use right-hand rule in this way. So here you have 2 vectors, A and B. Okay, so this is the first vector, this is the second vector. In our case, those vectors are, let me just write the equation again, V cross B. So this is another way of using right-hand rule. So in this case, V is the first vector, okay? B is the second vector, and the resultant is this one. Again, Q does not change anything. So this is one other way to solve, to get the direction. So let me get some results. For example, let's say you have a magnetic field going that direction, and there is a charge Q moving into that direction. Is there any force affecting on it? No, because the angle between V and B is equal to 0. So here, no need to use right-hand rule, because simply the answer is going to be 0. What if you have a charge, positive Q, moving that direction, velocity, and magnetic field is going that direction, B? Well, in this case, you direct your fingers with the direction of V, and then you try to move it toward B. So the magnetic field will simply be perpendicular on these two. So, for example, if these 2 vectors were located on this PowerPoint page, the vector F has to be perpendicular to this PowerPoint page, either inside or outside. Well, in this case, it's outside. Why I know it's outside? Because I use right-hand rule, and now I don't know how to draw right-hand rule. I don't know how to draw a hand. So let's say this is It's his hand. Okay. It's a weird picture, but so the way I'm going to do this, I'm going to point my fingers toward the velocity, and I try to rotate those fingers toward the B, magnetic. Of course, thumb will be out of the page in this case. So the force will be out of the page. Out of the page. Now, out of the page, you could either write it this way, or actually there is a notation for out of the page or into the page. Cross means into the page, and dot means out of the page. This symbol actually came from an arrow. So if your eye is here, you're going to see the dot. So for you, it's like out. And if your eye is here, you're going to see the cross, so it's like in. That's the meaning why this symbol is like cross and dot. Okay. So we're going to go through this again. I think it's these symbols are shown here. So out of the page, we use dots. Into the page, we use cross. Okay. Unit of magnetic field. So unit of magnetic field, we have some notations here. The unit of magnetic field, one of the units, actually Tesla. And you know Tesla, it's a great physicist, scientist. So Tesla is equal to Weber divided by meter square. Okay. But actually there is other units for magnetic field, but smaller. But it's not international. This is, how we have meter, kilometer, second. So this is not international system of unit, but it's still used. It's Gauss. It's small. So 1 Tesla is equal to 10,000 Gauss. 1 Tesla is equal to 10,000 Gauss. This table just shows us, the magnitude of typical magnetic fields. Source of for example, surface of Earth. As we speak, in your room, there is actually magnetic field around 5, 10 to the power minus 5. Now, this magnetic field actually, if you are closer to the north, let's say if you are closer to Canada, or North Pole or South Pole, this number goes up because it's stronger. Because in the UAE, we are kind of closer to the middle equator, so the magnetic field here is weaker. Okay, the surface of the sun is the magnetic field is stronger. Inside, actually, every time you think, inside our brain, every time we think, there are small electric signal passing through our nerves. So the value of the electric field created by our nerves is equal to 10 to the power minus 30. Now, recently in the last 20 years, we were able to detect this and actually make images out of this. So this is still in the start of the development. So every time you think about something, it's a very small current passing through the nerve. It's a signal, and whenever there is a current, means there is a motion of charge, a magnetic field will be created surrounding that nerve. So the magnetic field is very small, but now there are applications for this. Man-made magnetic field, for example, a typical MRI machine in hospital is around 1.5 to 3 Tesla. When I did my PhD, the magnetic field I used was 4.7 Tesla. But now we have strong magnetic field up to 30 Tesla. It's a man-made, all these man-made magnetic fields. Up to 30 Tesla, which is a huge number, very, very large number, used for research. Okay. Let me see how recording is going. Okay, let's continue. So we're gonna discuss some differences between electric field and magnetic field, some difference between how they behave in terms of force, motion, work, and things like that. So we're gonna again go back to previous chapters. Okay, so the way we define the electric field, we define electric field in terms of the force affecting on a charge inside this electric field. We said is equal to QE, and we already discussed in the previous slides a few minutes ago. The direction of the force is simply with the direction of the electric field or against it, either Q is positive or negative. But in the case of magnetism, it wasn't so easy. the direction of the force actually is perpendicular to the magnetic field. Okay, and also is perpendicular to the velocity. Sometimes we say it's perpendicular to the plane formed by V and B. Okay, so for example, if there is a charge, this goes into that direction, and this is a B. The plane formed by these two vectors is simply the page of this PowerPoint. So this is the plane. So the only direction that's perpendicular to this laptop or the PowerPoint is either out of the page or into the page. There is no other direction. But in this case, if you use right-hand rule to figure out the direction of the force, in that particular case, it's out of the page if Q is positive, and it's into the page if Q is negative. Okay. The second thing, again, we discussed motion. Electric field doesn't care if the charge is in motion or not. Electric field always exists. But in magnetism, no, the charge has to be in motion in order to be to create magnetic field. Now, in terms of work, the electric force actually does do work. Okay, when a charge moves from one location to the other location. We did maybe 2-3 examples in the midterm about this, right? We, for example, used conservation of energy to solve problems. Electric force does do work when a charge moves from one location to the next location. But actually magnetic field does not do that. Why is that? Because of the direction, right? Because the velocity goes this way. The velocity goes into one direction, but the force is perpendicular to it. The force is perpendicular to it. So the angle between, and if you go back to the definition of work from physics 1, is equal to F dot dr, right? So it's a dot product. It's cosine of the angle theta. In the case of magnetism, the angle between these two always 90. So cosine 9 is equal to 0, there is no work. Okay. So it does not do any work because the force is perpendicular to the displacement. Okay. So in a simple language, we could say electric field could actually speed up or slow down particle. Again, in the midterm, you had a question. One of them, if I remember, electron was placed inside a electric field. Is released. So what's going to happen to that electron? It's going to follow the electric field. It's going to get faster. Okay, it's going to, of course, going to go to the higher potential. Means electric field can be used to make charge faster or slower. But magnetic field cannot do that. The only job magnetic field will do is turn or deflect the charge. We're going to talk about this maybe in few slides after that. Okay. So one easy example here, an electron moving in inside magnetic field. Remember, this time is electron. So when we use right-hand rule, we need to reverse the direction of the force because electron is negative charge. So an electron moves through space as a cosmic ray with a speed equal to 8 million meters per second. The figure is shown. So let's look at the figure. So I need you to think about this figure as 3-dimensional. It's not 2-dimensional. So this is the screen. X-axis is coming out from the screen. Y is to the right of the screen. Z is up to the screen. So X is out of the page. So I need you to think about this as 3-dimensional because in cross product you need 3-dimension. So you have an electron moving out from the screen and you have a magnetic field is somewhere here. And we know the angle between now. V and B. Before reading the question, let's figure out the direction of the field, of the magnetic force on the electron. For a second, let's say it's proton, it's positive. So if it's positive, okay, you put your fingers on your 4 fingers on the V and you try to move or rotate your fingers toward B. In that case, the thumb will be upward. But because this is electron, so the force will be downward. So I need you to now think about that. An electron moving out from the screen and it will be experienced by a force that goes down, which means the electron moves out and then goes down, right? Of course, if the magnetic field is spread out over some distance, actually the electron will start to rotate. But this is a topic that we're going to discuss maybe in the next slide, okay? The question here, the magnetic field is created by Earth. Electron moving out from the screen, and it's a magnetic field by Earth, which is very small in this location. Angle is given. The question simply calculate the magnetic force on the electron. Okay, so we knew the force will be downward. So again, electron moving out from the screen, and a force will be directing on it downward. So of course, the path of the electron will not be straight out of the page, will go down, right? Will go down. So if you see it from the side, if that's the screen, if you see it from the side, electron want to move out like this, a force is down, so actually electron will move this way. So if the distance of the magnetic field was spread out over this region, this electron will move around like this. But again, we will discuss this in the next slide. So the question is, let's calculate the magnetic force. F is equal to Q VB sine. For the magnitude, we don't care if the Q is positive or negative. We take absolute value. Okay. So that force is equal to this value. So although the magnetic field of Earth is very, very small, but actually created a force enough to deflect electron from its straight path. Okay. And you will see this is very useful, because without this magnetic field that's surrounding our planet, we wouldn't be alive. Okay. Or maybe we would be alive, but with different shapes, different biological entities, and so on. Because there are a lot of cosmic rays, bombarding our planet. If there is no magnetic field, all these cosmic rays will simply hit us. Okay, hit our bodies, change our DNA, things happen. But because there's a magnetic field surrounding our planet, those will be deflected. So we're going to talk about this in a few slides after this. So this is now the topic. What happens when you have a charged particle moving inside the magnetic field? In this particular slide, moving perpendicular to magnetic field. Okay, so here it's a special case. You have a particle Q, positive, moving with a velocity v. That velocity is moving perpendicular to the magnetic field. So let's see what's going to happen. Very fast, in a simple language, what's going to happen is the particle will go around a circle many times, forever. If the v is constant, is b is constant. So let's see how this happens. So I want you to look at the slide now. The magnetic field is into the page, because cross means into the page. So magnetic field is going from your eye into the page, into this PowerPoint. Okay, let's start from the bottom part. So let's say you have a charge, positive, and this charge want to move to the right. Here the magnetic field is into the page. So what I'm going to do is, I'm going to use my right hand rule. Okay. And I'm going to try, so my right hand rule, sorry, my four fingers is with the direction of V, which is to the right. But I'm trying to go toward B, but B is into the page. So I'm going to try to move my hand into the screen. Of course, my thumb will be upward. So this will be force. That's why the force is drawn here. Okay. So what's going to happen? If you are that particle, what's going to happen to you? Well, instead of going forward in a straight line, you're going to bend. Your path going to bend. So you could apply the rule here again. So you're going to bend more, you're going to be here. In this location, this is positive. If you apply right hand rule, it's a terrible drawing, but useful. It's with V. Okay. So your thumb will be to the left. So if you keep doing this, you will see that that force always directing a point, which you in physics 1 you know the meaning of that force, the name of that force. It's actually centripetal force. This is centripetal force because it's always directing to the center. And according to Newton's second law, centripetal force is equal to MAC. AC means centripetal acceleration. But our force is not something from physics 1. Our force is the magnetic force, equal to Q times V times B times sine 90, which is equal to QVB, equal to MAC from physics 1, we know is equal to V squared divided by R. So we can rearrange that equation and we get actually the radius of that sphere. We get the radius of that sphere. I want you to look at this now. If m is constant and q is constant, let's say we have a proton. M is constant, q is constant. The larger the B, the larger the magnetic field, the smaller the circle B. And the faster the proton, or the larger the RB. And this is, remember this notation, okay, or remember this relationship. So R is inversely proportional to the magnetic field, but proportional to the MB. So our planet magnetic field in the North Pole, South Pole stronger. So when cosmic ray comes hitting us, those that try to hit and penetrate the North Pole or South Pole, or any region, Canada, North America, for example, those particles will move around smaller circle because the magnetic field is stronger. While if a particle, cosmic ray, try to penetrate the UAE area, those particles will move around a bigger circle because the magnetic field is slower. Right? We're going to talk about this again later, but the equation in front of us, so I thought it would be good to relate things. Well, in physics 1, whenever you have things that going around a circle, it's always a good idea to talk about angular speed, right? So again, physics 1, angular speed is equal to v divided by r, right? So v divided by r, you could use our previous equation, find v divided by r, so you have qb divided by m. Because I could rearrange that equation and dealing with v, right? So v is equal to r qb divided by m. Personally, I don't memorize all these equations. I just know Newton's second law. And I know the force is equal to QVB, so I could get all these equations in no time. Okay. Again, as I mentioned, when you have something moving around, you could talk about omega, you could talk about a period, the time required for one oscillation, one circle, one movement in a circle is equal to 2 pi r divided by v. From where this came? Well, v is equal to the distance passing, the distance covered in one circle. So this is distance, which is 2 pi r. The time that need for the particle to go around the circle is t. So t is equal to 2 pi r divided by v using our equation. So we know now the period actually goes up when b is weaker. So we could talk about this relationship, but the origin of this simply is the magnetic force and application of Newton's second law. Now, what happens if the particle moves inside magnetic field not in 90 degree, because that's a special case, right? Well, if the angle was not 90 degree, instead of a circular motion, it's going to be a spiral motion. So we need to discuss this. Okay. Let me pause it for a second. Okay, let's move on. Here we have a particle that moves inside magnetic field in an arbitrary direction, not 90 degree. Okay, it's a general. So I need you to focus on this picture. Again, this is 3-dimension: x, y, z. You could think about it x moving diagonally this way, or you could think about z coming out from the page, or x coming out from the page. So it's 3-dimensional. I need you to think about 3-dimension. In this case, magnetic field is going toward x. So we have actually bx. We don't have by, we don't have bz. Particle moves into xy plane. Originally, particle moves this way with a velocity. Now, velocity has 3 components because 3-dimension. We have vx, we have vy, we have vz. So do you think the component Vx has any effect when it's moving inside Bx? The answer is no, because Vx and Bx, the angle between them is equal to 0, and according to that equation, F is equal to QV cross B. So if I apply this equation for Vx, it will be Vx cross Bx. So the force in the x direction will be equal to 0, right? Will be equal to 0. So there is no magnetic force on the x direction. But remember, you have these two components perpendicular to x-axis. So their addition, we call it perpendicular component of velocity. Their addition, actually, let's call it perpendicular, is equal to square, right? Vy square, Vz square. Now, actually, this value, it's perpendicular to the magnetic field. So because it's perpendicular, so a maximum force will be applied on this. So in this particular case, so this is a special case in the previous slide when V was perpendicular to magnetic field. We saw the particle just moving around like this. If it's not perpendicular, we still have a circle. This circle was there or is there because we have a component of velocity which is perpendicular to the magnetic field. So this is perpendicular to magnetic field. But we have another component which is not perpendicular. So that component will simply drag the particle to the x-axis. That's why it's a spiral in moving toward x. Why moving toward x? Because there is this component that dragging this particle toward x. So it's moving around the circle, but like in a spring. It's a spiral motion. In a spiral motion. Okay? So all equations that we have in the previous slide, every time you see V here, you see V here, V here. If you apply it in a general way, instead of V, you gotta say is equal to the perpendicular, which is this, which is that one. Okay. So that's what I'm saying. Mention all the equations for the special case. Just simply you change all the V's into the perpendicular components, the sum of the perpendicular components in a vector notation. Okay. So some examples of particle in a non-uniform B. So we already discussed what if the B goes up or goes down, what's going to happen. So one of the things that we learn is, for example, in this particular case, looks like magnetic field here is strong. Magnetic field here is strong. Magnetic field here is weak. How do I know? Well, there is a particle moving around, moving in that space. Here, the radius of that circle is small. Here is small. According to the equation that we had it before, look at the equation R is equal to mv divided by qb. So R is equal to mv divided by qb. We see the relationship between B and R. So here R is small, the radius is small, means B is large. But here the radius actually get bigger. The radius of the circle get bigger, means B is weaker. This actually, in research, this is called a magnetic bottle. Okay, so it's a region created in such a way that they play with the magnetic field, very strong here, and weak here. So what happened? This particle moving back and forth, and is not allowed to escape. So this is called magnetic bottle. Okay. This is again the picture of our planet. So we said our planet behave like a magnet because there is a magnetic field around our planet. So we have actually the south is here, south magnetic pole, and north is here. And we know that here magnetic field is strong, here magnetic field is strong. That's why you see the radius small here, but here the radius get bigger. So those particles moving around without actually hitting us, without going and penetrate. Some of them still, penetrate the Earth, but most of them is actually suspended or moving around our planet, and that area called the Van Allen belt. Van Allen belt. That's the reason when astronaut people go into the space, or even if you are a normal pilot, you fly, you actually you have a bigger exposure to those cosmic rays. Okay, as a pilot, I'm not sure, but they have a certain number of hours they have to serve, and then they have to take rest and things like that. They have to be checked annually. So as a person, because we evolved for million of years, we have a certain threshold we could tolerate, certain threshold of receiving those cosmic rays. But if you get too many of those, things happen. That's why when people go into space, they have a special suit, right, to protect them from these harmful particles, high energy particles. Now there is a phenomena in the North Pole and actually in the South Pole. It's called aurora, or they call northern lights. The concept of these northern lights simply is these cosmic rays, when some of them penetrate the atmosphere and ionize the air, and when it's ionized, the ion actually produce this color like greenish, yellowish. So people in the North Pole, or North Pole mostly, they didn't know this, so they have some kind of a spiritual connection to those lights, and they consider these are their ancestors died long time ago, and they light their path in light. So they created some comfort feeling when they see this kind of light. But of course, science explained it. It's simply the ionization of atmosphere gas from these cosmic rays that penetrate the planet. Now, the reason why we don't see it here, first, magnetic field is weaker. Second, we don't have too many of those particles penetrate. But in the north, they do, because the magnetic field, if you actually look at it, the magnetic field is kind of this way, right? So there are more chance for particle to actually get closer and penetrate the atmosphere, or getting closer, so ionize the air, and then produce these colors, beautiful colors. Okay, we're gonna solve this question, and I might maybe make this one like a part one of the video. So here we have a proton moving perpendicular to magnetic field. A proton is moving in a circular orbit, radius 14 centimeter, in a uniform 0.3 Tesla magnetic field perpendicular to the velocity. Find the speed of the particle, of the proton. So in this case, again, I'm not one of those memorizing equation. I cannot start this way. I'm going to start with the Newton's second law. I'm going to simply say F is equal to mac. Okay, you don't even have to write this. Our force is qvb sine theta, which is 90. In this case, equal to mv squared divided by r. Okay, so this is simply v is equal to qb r, big R doesn't matter, divided by m, which is the same equation. Of course, here we need to know two things. We need to know the charge of proton, which we know, and we need also the information for the mass of the proton. So this is the force affecting on it. Now the question also asks, what if an electron rather than proton moves in a direction perpendicular? So what's going to happen? How the answer will differ? So I need you to think about that. Okay, this is the equation. Instead of proton, you are using electron. So think about that and see how the result would be. So I'm going to finalize this. I'm going to call this one part one.